So good afternoon, everybody. I'm Massimiliano Schwarz from the Bern University of Applied Science, Switzerland. And I'm really honored to be here. Thanks for everything, for the project collaboration, and all the people work on. And I will just present some of the topics and work we share with people in New Zealand, but also within the group. So the hard work was done especially for our students. One of them is Faiko here. Marcelin is also here. We have another PhD student working on the root distribution, and some bachelor students that went to New Zealand to do the field work, the hard work. In our group, we work a lot about tree roots. So that's where we start most. So this is kind of passion we share with trees, not just digging roots. But we're really look at that, also trying to translate the information we have at the small scale to really practical application in terms of quantifying ecosystem services. That's the second term in the title. And the third term I put in the title was probability. It has important link between the two scale, if you want, small scale, theoretical, scientific, and the big scale with the practical application. In the picture, actually, you see something that could be a picture from New Zealand nowadays, but that's actually what we had in a lot of places in the Alps, like 100-200 years ago. And on that condition, there was a period, especially in the 19th centuries, in the beginning of the 19th centuries, with a lot of catastrophe going through the Alps. And that was really an important political trigger in many countries, Switzerland, France, Italy, even Austria. And so again, just to make the context where we are working on now in Switzerland, but in the neighbor country too, this is like the temporal dynamic we can saw in the landscape in the last 100-200 years. Those catastrophes I was mentioning before, floods, debris transport, debris flow, lead to the formulation of the first forest law in Switzerland. That's the first time that was recognized as forest has an important role in regulating risk due to this kind of natural hazards. And that point, the key word was sustainability. So use land, use the forest in a way that we can enjoy products for building, from wood, and also have protection from natural hazards. So that's what happened in the 19th century, beginning of the 20th centuries. There was a lot of afforestation and no management for a lot of decades. Until the 80s, 90s, where we realized that no management a really unstable and not sustainable system of forest, because they started to have a lot of problem with storms breaking the forest stand because they were not managed and not stable, falling from bark beetle problem and so on. That's why then in the 90s we had the first law that assessed the importance of protection forests, and the most important thing that was the first money for forest management. So in that law, the government put money and said, private or forest owner, you get extra money as ecosystem service in the way that we have protection forests. The second question was then to have guidelines to tell people how to manage those forests to target the aim of protection forest. And then recently, people started to fight for the money. So there was the need of like a standardized way to define which are the protection forests in Switzerland. So we have a national map for those protection forests. That's a short history of like the context we are working in, dealing with forest slow processes and risk. And as you can imagine, we have different type of issue. So not only related to water quality, and sediment in rivers, but also direct hazards for villages and roads, and indirect hazards due to large wood debris or the transport. I have not the time to go into detail, but give you an idea of the complexity of the different type of problems that we have with the same kind of processes. This schema is what show you from the left to the right, like increasing complexity of the type of understanding a process. That would mean in spatial and scale. So left would be a national level, right would be for a single village or house, using different methods. So really general information of soil and precipitation. And when you go more in detail, you want to know exactly which type of soil, which kind of frequency of rainfall, and so on. And the other level are like different product that you can get to solve different problems, looking at one or more scenario of the return period of your triggering process or factor, looking at different scenario of vegetation, including vulnerability and calculation of risk and cost benefit analysis and so on. So just to put the context where we were aiming in the project and the discussion with Chris in STEC was really a kind of what we call the impact analysis of some measures. So in that case, if you put trees, how would be the effectiveness basically of these measures? You can reverse that approach looking what happens if you take out the forest. So you have a wildfire. It's the same kind of approach. So as Chris already introduced, we had like three main topics in this collaboration. One was the upscaling or route reinforcement with all what Chris already mentioned. Then the implementation of this information of the spatial distribution of route reinforcement in a slope stability model, test it in New Zealand condition, and then use that model to do the impact analysis of different type of measures. And just to have an idea which kind of process we are speaking about, the shallow landslides, I always like to show the movies. I have two movies of real live landslides. So in that case, it's really a slow triggering shallow landslide. All the forcing on tension and sharing are basically already gone. So there is no resistance from soil or roots, in this case, no roots, from sharing. Everything now is going on compression, compressive forces. So when the maximum possible pressure is reached from that mass of soil, then you have the run out of the mass. And it, you can imagine the link between what you see after a rainfall event and this type of dynamic. It could be really fast, everything in 1 second or a couple of seconds, or could be really slow but continuous, like this. And this, for me, is really important to then try to understand what is the influence of having some roots in this map, which, as we heard this morning, if you look at the statistic, they are usually not big volume or areas. We are speaking about 50, 100 square meters. And in that range, you can start to understand how roots on the sharing plane or in the tension crack or in that compression zone we saw in the video can act to stabilize those mass movements. So one of the first important starting point to characterize the effect of these tree roots from the mechanical point of view is to measure the pull-out force. So this is kind of result we get for poplar. So on the x-axis, you have the dimension of the roots, and on the y-axis, you have the tension force, the maximum when it breaks. And so here is already the first step where you implement probability to characterize how probably is that a root break reaching a certain force, which is not always the model like the line, but it has certain variability. And so from that point, you start to implement probability to characterize the root reinforcement with a machine done by Jaka Taikanayake, I have to mention, was one of the best pull-out machine in the world. Then, as Chris mentioned, we need to characterize the three-dimensional distribution of roots. So how many roots, how big are the roots from which tree species? And it was really an honor for me, but also I think for our student to contribute to work on this topic, which Chris were working from decades. I think we're basically, as Chris said, there are some data for small trees, but this understanding of how to change the root reinforcement with the years. Once you plant the stake, the poles, how many years it takes to have certain amount of root reinforcement. And this data set now is really complete, and I think it can help to understand this kind of dynamic and effectiveness of the measures. So in the next part, there was the work done by FICO, validating the slope stability model. So in our case, we use more a physically based probabilistic approach, where we try to put factors, understanding which factor and parameter influence how much the process. So here's an example of the comparison between the modeling data with the scars data, the blue point, for a certain return period event. In that case, it was validated for a defined rainfall event. Using the same information about the spatial distribution of trees done by Raphael, where actually all these small dots define the position of the trees. And then we need also the information about the dimension of the tree to then map actually to model the root distribution on the three-dimensional way. That's how basically this area looks like. And so one of the main goals then was in the third part, where Marcel is working now on, is to compare for different type of scenario. We can discuss later why different type of scenario eventually. We can use the actual vegetation and compare this with a ideal vegetation, filling up some criteria to define this ideal vegetation. And comparing the probability of this landslide map, we can come up to understand how big is the impact of these measures on the landslide susceptibility. For example, on the left side, you see this difference between actual vegetation and ideal vegetation or potential vegetation. So at the farm scale, it could help really clearly to spot out where are the hotspots where you can invest some money to reach a certain target of stability. And in the same kind of approach, in analogy, we can try to do that also for bank erosion using the data on the trees along the rims. So this is the kind of product that could be reached with this approach. With that, I'm finished. Thank you for your attention.